Okay, so overall review. Let's just kind of start at the top of chapter 2. I also, hopefully I'm sharing the correct screen because I have the test over on the other screen. Okay. So, acoustic variables, pressure, density, and distance. We see our pressure, density, and distance down here a little bit better. I'm sorry, you can't see my hand down here a little bit better. This, of course, is our mechanical longitudinal wave. And when we talk about pressure, well, we're talking about how much things are squeezed together is really pressure. So there's a high pressure there, low pressure there. It is really the same as also saying density. So I'm just going to take the P away and replace it with a D. Density, density. We have high density in the compression, low density in the rarefaction. And then distance. I want to make sure you guys understand what distance means. It also means, it's the same as saying particle or molecule vibration. Here I've drawn, nicer color. Here, I basically show that this particle is vibrating back and forth. It's vibrating a certain distance, and these are, realistically, they're like microns of distance, but they're very, very, very tiny distances that they're actually traveling back and forth. But this is what a wave is these vibrations here. If we were to look at a transverse wave on top of a pond, distance is up and down. Particles wave up and down, and those distances are considerably more, but that is distance. Distance and particle vibration are the same thing. So acoustic variables, pressure, density, and distance. I noticed that I was actually looking for a filter, and I'm trying to make myself look better. Thank you very much. Okay, now those let's see. What do I just say? These are variables. So parameters. I'm going to put up here. Acoustic parameters are, these are better measured with this type of wave. So let's see, we have one cycle here, right? And let's see, we could measure period T.
We're still missing some.
Missing what?
We're missing some students.
This will be recorded. I wonder if they didn't go to the other class.
They did, because I was too.
All right. Well, if they missed the first 5 minutes, it wouldn't be hard to go back and catch the first 5 minutes on YouTube. Okay. So acoustic parameters, that's period. We could also say, well, no, frequency is going to be all the way to the 1 second mark. Let's see. Frequency in this case, 1, 2, 3 is 3 hertz. Because there are 3 complete cycles here. 1, 2, and 3. Yeah, within 1 second, right? Hertz is how many cycles in a second. How many? Yeah, how many cycles in a second? Let's see. Amplitude. No, we haven't really measured amplitude. We just know it's here, right? That is our amplitude, how strong the wave is. Power. Okay, well, you know what? Same thing. We can measure power where we measure amplitude. Intensity. Intensity is going to be power divided by area. We're not going to work out any math on this, guys. Just remember this. Area goes down, intensity goes up. One good example in ultrasound of the area going down is at the focal point. So when we put a little caret on the side of our screen, what we're actually doing is taking a beam of sound and narrowing it at that point. So in essence, the area has gone down, the intensity has gone up. Like I said, no math. Wavelength. Looks like the same measurement, except it's a length. The other one was time. And propagation speed. Millimeters per microsecond average soft tissue. Longitudinal, in phase out. Okay, let's kind of have a nice little, I was going to write all that down, but you guys, it's right in the book. I'm not going to write it down. Before I go any farther, so for each one of these, period, can you adjust it? What creates it? Does the medium create the period? Does the sound source create the period? Same thing with frequency and intensity, power, and all of amplitude, wavelength, frequency, period. What can and can't you change? What is determined by the source and what is determined by the medium? Sometimes it's a little bit of both. But just remember those. I'm not going to go over all of that in detail because that would just be starting completely over. I do like this though. I'm going to, let's see, 5. I think it's this one. Yes, okay. So on the screen you have 2 waves. They're both the same frequency. They both happen to be the same amplitude, although that doesn't necessarily matter. And they're totally in phase, right? So the resultant wave, of course, is going to be bigger, obviously, right? This is constructive interference. Oh.
Is this a review?
Yeah.
Okay.
Yeah, this is all review, sorry. And okay, it survived. That one just went away on me though. So anyways, this is going to show constructive interference. Let me just really, only because I kind of feel like I screwed it up a little bit the other day. I screwed it up a little bit trying to show you another way of doing this, and it turns out I didn't really like it. And I have a feeling if I didn't like it, you guys didn't like it either. Okay, so, oh, Jesus. Constructive interference, destructive interference. Understand that? This will make a bigger wave. This is perfectly destructing. Doesn't happen very often, but this is perfectly destructing. Therefore, this will create no wave at all. If waves are at a different frequency, let's say we have, they're in line here, but now I've changed the frequency here. Let's do it to about there. So now I have, whoops, didn't mean to change that. Now I have two waves of different frequencies. When they lay over each other, let's do it right about here. That's actually perfect. Sometimes, whoops. Sometimes they are destructive. You see that a peak lined up with a trough. And sometimes they are constructive. So it goes back and forth. We call this a beat pattern. And so there, in that case, you know, it's constructive interference, it's destructive interference, kind of at the same time. So you get a wobbling back and forth of constructive and destructive. Okay, so I don't want to spend too much time doing this. Just want to do like, so period, frequency. If frequency goes up, what happens to period? Know that. Amplitude, power, intensity. Wave length. If frequency goes up, what happens to wave length? Speed.
The wavelength is shorter.
Frequency goes up, yes. Speed of sound, obviously there's some numbers there to know. I wouldn't say memorizing all of the speeds except for the soft tissue, that's one. But do memorize that air in lung is by far the slowest. Fat is slow. And bone is fast. Remember those. Remember, density actually decreases sound. It affects sound, but it actually affects it in a way that we wouldn't think. It decreases sound. Stiffness, higher stiffness, increases speed of sound. It's also called bulk modulus, or it's also called compressibility, which stiffness and bulk modulus both are, the higher those numbers go, the faster the sound goes. Compressibility is a little bit saying it in the opposite way. If it's higher compressibility, it means actually that it's less stiff. So just don't get confused on that, but those all really mean the same thing. And that's it, guys. I don't, remember the one, I already gave you one of the questions that's literally on the test. That's basically what you're going to find. Multiple choice. It'll be easy. Okay, let's get on with today's day. Let's see, open recent. Oh gosh. Is it intro to Doppler? Let's find out. No. Yeah. So today I want to do two things. We're not going to finish 18. I do want to talk about a few things, and then I want to get into Doppler. You're not really ready for the physics of Doppler, but the application you're ready for because we're starting to scan carotids, right? And it's really hard to scan the carotid without using a little bit of Doppler. So I'm going to teach you a few things about how to use Doppler. Oh, and this is the wrong one. File, open recent. That's the wrong one. I just put a lot of work into this, and I really hope it's there. Oh, there's my kitty cat. All right. And I never know exactly where it puts all this. Seriously, this is not. There we go. It is in pictures. What did I see? Okay. Insufficiency physics. That's the one. No, it's not. Chapter 18, part 2. Now I know I've got it correct. Okay. Sorry, guys. Can you forgive me?
No.
Okay. And where are my controls? Oh, God. Open. So somehow this got saved as an image. Open sketchbook. I could fix that, though. Here we go. All right. Thank God. Oh. See, I've actually made most of my mistakes prior to you guys seeing me make them, so it's actually not too bad. So some of this is kind of review. This is next chapter. You're not going to be tested on this tomorrow. Just remember, conservation of energy means it cannot be created or destroyed, but it can be misplaced. In other words, you can lose energy to heat, for instance. I could lose my sunglasses, but it doesn't mean they're destroyed. They're just not in the system anymore. And so if we're talking about vascular, the system of vascular is what we're talking about. That energy still exists. It's just gone somewhere else. Okay. So if we increase one kind of energy, in other words, kinetic energy, the energy of motion, then we must take from another, pressure. But note, this gets a little confusing, and I think Rachel talked about this or noted this the other day. This pressure energy is like air in a balloon. It is static pressure. It is the pressure pushing out in all directions. Now, it still gains energy from the heart. The heart stops, your static pressure is going to go down to zero. But there is a bit of a difference. It gets a little wonky in there. There's pressure gradient, and then there's static pressure pushing out in all directions. Still provided by the heart. Static pressure put down all the time. Though not destroyed, energy is lost, mostly heat in a system. Pressure downstream of a stenosis never goes all the way back to pre-stenotic levels. Changes in inertia also steal energy from a system. So, you know, we've learned through Bernoulli, it's right there actually, that kinetic energy, the velocity, 4 times the velocity. So they're talking about, that's talking about kinetic right here. your kinetic energy, a change in your kinetic energy has to force a change in the pressure energy, the pressure density. Is that a good way of saying it? Pressure density? Pressure energy, anyway. So when velocity increases, pressure decreases. And that is an absolutely true statement. I just thought of something that I'm not going to bother you with right now, because the last thing you need is, that is an absolutely true statement. When velocity increases, kinetic energy increases, pressure decreases. So, well, I'll show you up. I've got a picture up top. Poisson is not even mentioned in your book, although it's probably in your other book. It should be. I don't know if it's ends with an I or an E. It doesn't matter. Oh, I'm sorry. Bernoulli. Short stenosis only. Bernoulli only works on a short stenosis. Poisson is a long stenosis, or simply a long vessel. So before I had like what essentially turns out to be a long stenosis. Bernoulli does not affect a long stenosis, simply because Poisson's equation, the volume flow rate, now becomes more prominent. So long stenosis or vessel, the volume flow rate Q. So Poisson's is usually designated by Q in milliliters per second. And then we have this equation. Once again, don't worry about the equation, worry about just a few things. Okay, so do worry about the equation, but don't worry about like thinking, oh my God, I have to work this out. And no, we're never going to do this on a test. Remember, anything that happens up on top, arrow, if it goes up, volume flow goes up. So if the pressure gradient, your heart beats harder and faster, your volume flow will go up. Pi is pi. Radius, if radius goes up, volume flow goes up. And this is significant. The number 4 here means to the 4th power. So a small change in the radius of a vessel can make huge changes to volume flow. So that's the significance. That's the major, probably the biggest significance of this equation is r to the 4th. 8 is just a number that they've derived. Length, well, if the length goes up, in other words, the longer and longer and longer, whoops, that's just god awful. In any case, the longer the tube or the longer the vessel, the more, think about, it's more walls, more friction, more distance to push the blood through. Volume flow will go down. Funny looking N, that is viscosity. If viscosity goes up, Q goes down, volume flow goes down. Of course, viscosity is like honey. Honey is viscous. Water is typically not very viscous unless it's frozen. Oh, I have a couple of things over here. Yes, basically Poisson simply asks the question or answers the question, how much fluid will flow? Bernoulli's, if I can jump back to him for a second. Well, Bernoulli's is basically asking or answering the question, how much is pressure going to drop? or how much lift is this wing going to give me if I was an airline pilot? So Poisson is really, and this is probably why your book is dropped. They're basically, it's not that the physics test is dumbing down, it's just that it's evolving over time. And there are certain things that really, do we really need to know Poisson's equation? I think it's useful, but it's just a far easier way of saying it is a pressure gradient is equal to flow times resistance. Well, hold on. Flow, I've just rearranged the equation here. I put everything into a triangle here, and I realized that I can divide, dang it, that's not what I meant. I could divide pressure by resistance to get flow. So flow is pressure gradient divided by resistance. Well, this is the same thing. This flow, pressure gradient, resistance is a simpler version of this. Flow is, well, flow, Q. So that makes sense. Pressure gradient, well, it's there. We might have ignored a couple of other things, but the pressure gradient is there. And resistance, well, viscosity is certainly resistance. Increasing length is certainly resistance. So really, this is the same equation. Flow equals pressure gradient over resistance is saying the same thing in just a simpler form. Now, the reason why we put it in this form, or the book wrote it in this way, and I really don't like this way because this is kind of I really don't like this because I feel like this is a false premise. Pressure gradient is equal to flow times resistance. Well, yeah, pressure gradient's created by the heart though in our situation, but mathematically this is perfectly straight because basically we've gone from pressure here is flow times resistance. So the triangle still works, the math still works here. Flow times resistance. The reason they put it in this form is because there's a similarity to a simple law in electrical engineering. It's worth mentioning. Why is it worth mentioning? For the sole purpose of getting that answer correct on the SPI. And as far as I'm concerned, it is the only reason why it's worth mentioning, because there are similarities between flow through pipes and electricity through wires. It actually is really, the mathematics is very similar. And I don't understand why we have to care, but apparently we do. So let's talk about it. Similarity to a simple law in electrical engineering is worth mentioning. Ohm's law is voltage times equals to current times resistance. Well, flow and current are both terms that can be used in a river. A river flows and it has currents. It's the same, it's very similar word, right? And of course, resistance and resistance are the same, of course. And resistance is futile, apparently. And then voltage and pressure gradient. Well, in electricity, everyone's afraid of volts. High voltage, it'll kill you. Well, yeah, it's actually not the voltage that kills you. Voltage is simply potential. Pressure gradient is kind of your potential energy. The flow is the kinetic energy, and in the In the case of electricity, it's the current that kills you. Now, high voltage just happens to produce high current, but if you have equal voltage, you won't have a current, you won't die. And that's why people can actually work on high voltage lines up in the air as long as no current goes through them, they're fine because they have the same voltage, which is really kind of weird. You could have tens of thousands of volts in your body and not explode until you become grounded, and then you explode. All right. So that was a little bit of chapter 18. Chapter 18 ends with venous hemodynamics. We'll do that next time. We don't need to. We're looking at carotid arteries right now, so we don't need venous hemodynamics just yet. So I'm in no rush to get to that. What I am in a rush to get to is to look at a few things on Doppler. Now, this is fun stuff. We're going to learn more about this later. But for now, this is just an introduction so that when I say things in lab, they at least make a little bit of sense. Oh, come on. Okay. Where to start? Actually, after doing all that, I'm now going to zoom in. Doing all that, I'm going to zoom in. Okay, so I've shown you this before. We've looked at our vessels before and looked at this plug flow here, parabolic flow, but both of those are laminar, right? And we've had some beautiful laminar flows in lab. I'm sure everyone has beautiful laminar flow, but we have to set up our machine correctly in order to get that. So we have nice laminar flow here. We probably have laminar flow inside of the stenosis, but it's just going really fast. And then turbulent flow here. We can't measure pressure directly with ultrasound. So yeah, there's a pressure drop here, but we're not going to measure it. This is turbulent flow. This is still turbulent. Some people call it disturbed because it's not quite as turbulent. And so we're going to look at a little bit. I wish I didn't have flow going this direction, because when we do a carotid ultrasound, it's going the other way. It's just, but the principles do not change, so just keep that in mind. Okay, so we know. I'm going to just actually. Z. Get a little helper here. Laminar. Turbulent. And we'll just stenosis, velocity increased. Okay, that's stenosis velocity increase there. Okay. So starting over here, we see beautiful color inside of our color box. It's all red. Well, it's an artery. So we've decided to make it red. The machine won't do that for you reliably. Sometimes it will, but it will not reliably do it for you because the machine's dumb. Flow is actually faster here in the middle. And if your machine is sensitive enough, sometimes we could actually see the difference in color. I'll get to that in a bit. Then we have a stenosis. Well, in this stenosis, in this color box, we're seeing the plaque here. And so since we see the plaque, we know there's going to be a stenosis. But guess what? Sometimes plaque is isoechoic to the vessel. In other words, The vessel's pretty much hypoechoic or anechoic, so is the plaque. Sometimes it's invisible plaque. And so we have to scan carefully in order to find that invisible plaque. Usually it's seen, but sometimes invisible. And then, so it starts off red, and then inside of here, I have these colors. Color myself. Dark blue is fine. Okay. We have these myriad colors, or these reds and blues all mixed up together. And I did something different over here. Over here, I have mostly red with a little bit of blue. And we're going to zoom in a little bit on both of these to show some differences here. Over here in the plaque inside of the stenosis, it goes from a darker red to a lighter red to a yellow to kind of a bluish green and maybe a little more darker blues in here. Just wanted to add that. So it goes from darker to lighter colors to lighter color back to a darker color. Over here, we have a color change as well, but it goes from a dark red to a thin layer of black. Look at that. If you look carefully, there's actually a thin layer of black around this smudge of blue. These are two different phenomenons happening, and so you have to pay attention to know that. This is something that is not well taught in a lot of ultrasound schools, so there's a lot of people who actually don't really know it, or they don't practice this well enough. Because what we have here is aliasing. And I'll describe what aliasing is in a second. Over here, we have reversal. So reversal is easy enough. It literally means reversal of flow. So in other words, there are patches of blood that are swirling, and when they swirl, they go backwards just for a little bit, and then they go back forwards again. So there's essentially backwards flow. Of course, I'm using blue on blue. That's really helpful. Let's try that again. Backwards flow, and then maybe it straightens out again. A little bit backwards flow here. And let's do just backwards flow like this. Okay. Hopefully I didn't draw too many arrows. In fact, let's get rid of those last couple. Just concentrate on the bottom one. So when we see this, flow is running backwards. Now it could be because of turbulence. In this case, we have turbulent. Turbulent reversal. Sometimes blood actually hits a higher resistance area, and actually you have a reversal of flow of the entire vessel. So it goes 2 steps forward, 1 step back, 2 steps forward, 1 step back. That also will show red, blue, red, blue. What I've drawn here is a little more, looks more like turbulence. Okay. So what does this mean? I'm going to come over to one of our scales. In fact, I drew this arrow in to remind me. Color scale. Let's look at our color scale first. Oh, and I will actually write this in quickly. Both scales, all right, I'll just go ahead and write this down. Spectral scale, okay? Both are controlled by PRF. So pulse repetition frequency in Doppler is controlled by us. It is the top left, well, it's the farthest left soft key is our PRF. So when we have excess aliasing, we can change our scale. Or if we don't have enough information, we could change our scale. So the color scale is in centimeters per second. When you guys are doing your carotids, I think a good overall scale might be 18. It really, so color scale, we'll talk about why and everything, but it's actually kind of inaccurate. I don't know why it says 18, like 18 is a good scale, because quite frankly, your blood's traveling more like at 80 to 100 centimeters per second. So I've never understood the scale on color scale, and I've looked it up and I've never really gotten a good explanation. Okay, but what matters here is this. What matters is that I didn't leave myself a lot of room. All right, I'm gonna have to erase my little. Okay, the rest of it's fine.
Hey, Kurt.
Yeah.
So is aliasing creating an artifact?
It basically is. It really is. It's an artifact, and it's a way of the machine dealing with going off the scale. Really, it's off the scale. It's aliasing.
I just wanted to make sure, because I looked up in my medical journal, my medical dictionary, and it said that it happens because of portions outside of the field of view getting scanned and being placed in an incorrect place within the field of view.
Yeah, it's not so much field of view, but it's the scale of this. So, like, if I have a scale of set to 18 and 18, and suddenly I go, well, let me get to it in just a second. But you're correct. Here we have that black line. Now remember, we had I had a little bit of blue inside of well, okay, I just wanted to quickly, I didn't want to jump back and forth here. We have this black line between the red and the blue. You know what? That's just not working. There we go. There was a black line between the red and the blue. And I said, that shows reversal. Well, there's the black line. It's literally, almost all color scales have this. Some of them don't. Those are stupid ones, but they almost all have this. And so if you're red, that means you're traveling in a certain direction. Actually, as this is set up, red is positive. Positive simply means coming towards you. I have another picture that's going to help us with that. Negative is down here. That means going away from you. So we told the computer that we want this vessel to be red. So we may or may not have hit the invert button. But so we have red here. And there's a reversal. So it's traveling in the positive direction, but then remember it swirled backwards. And when it swirled backwards, it went down to here. So it started in a positive direction, it changed direction and went down to here. So it went from dark red to black line to dark blue. So when we see that pattern, dark red, black line, dark blue, we know that we're not dealing with aliasing, we're dealing with the reversal of flow. It's really important to note because people have gotten confused and called things aliasing that are not. Now, aliasing, that's funner. That's a fun one. So in the stenosis, you'll note that I had, going into the stenosis, it was red. And then there was some kind of greenish yellows and then more yellow. And then light blues, aqua blues here, and then into dark blues. The flow on this scale, as it is set up now, the flow started out about here. Average flow was somewhere in a deep red color. As the velocity increased, it became a little more orangey yellow. It got up to yellow here, and then the computer doesn't know what else to do with this. It's like, okay, well, I have a scale of red being the slowest flow, yellow being the highest flow. So now what do? It's gone off the scale, off the charts, off the scale. And so the computer just says, all right, I'm going to go around and start over and go backwards through this scale. So that goes from yellows to blues, to light blues, to dark blues. So if you don't want that to happen, and so sometimes we do want that to happen, by the way. If there's an actual stenosis, you want aliasing. Your eyes are supposed to be drawn to that, and the doctor should say, oh, look at that, there's aliasing there. If there's not aliasing, then we take our PRF, we turn it clockwise, and we say, you know what? It looks like 18 was too small a number. Let's make it 25. 25 and negative 25. Now, let's say our flow is in the red, but it stays in the red because now we have more. We've basically, by increasing the scale, how would I say this? We've added more numbers. We've added velocity. That's a good way. Oh, so much better if I just do that. Added. Okay, not much better. We added velocity values. Hopefully that makes sense.
So we're basically increasing the range from what the computer can look at.
Yeah, we've basically said, okay, computer, well, when we were down in a low PRF, a low scale, we had You know what? I'll even put in hash marks. We'll put in imaginary hash marks for a low PRF scale, and so there's only so many velocity changes that we can go through before alias. Oh, let's just write that in. Before aliasing occurs. By increasing the scale, I'm basically adding more imaginary hashtags, little hash marks here, and now I have more values. So let's say before I had values between 1 and 10, and now I have values between 1 and 20. I've basically added velocity. Now, that's good if I want to get rid of aliasing. It's bad if I want to see a little more detail in how the blood flows, because by adding velocity values, I'm minimizing the differences in between each value. And so it's a balance. If you want to show aliasing, take it down and force that aliasing to occur. We like this sometimes. If we don't want aliasing, it's going to turn it back up. By turning it up, we lose some detail. Because you could imagine more hashtags, smaller increments, we could lose some of the greater detail there. So let's go back to this picture. And we could see there is no black. By the way, that black line on the scale itself baseline. It's another form of a baseline. You could see when I drew this in here, there's no black around it. It goes from one color to the next without a baseline in between it. This one here has that baseline shown. Okay, so we have aliasing and reversal. In this case, it looks like turbulent reversal. Let's look at our pulse wave and see what that means. Awesome. We are doing awesome today. So I have, once again, I have another baseline. And I have a scale over here. Now, a little tidbit of information. Color scale is completely inaccurate. This scale is accurate. And it's just a different, it's both Doppler, but it's a different way of doing Doppler. So, waveforms that are more or less like this, clean, within the scale that we have, are probably a nice color of red or blue, whatever you have it, and probably laminar. But when we hit this stenosis, our velocities go past 200 or probably 250, I have on the scale. It goes past 250, and once again, we do the same thing. Computer doesn't know what to do with this, and rather than just not show it at all, it shows it up on the bottom. So we could do, on this particular one, it looks like I could probably take my baseline and move it down. If I move my baseline all the way down, I think this peak will fit. And by moving the baseline down, I'll have essentially more hashtags on top. I can probably go up to 350, maybe 400. Let's just say 400 centimeters per second if I move my baseline down. So that's one way of dealing with it. And if it's not dramatic and you have room, go ahead and move the baseline, and then you're done. The other thing that we do, once again, PRF, so both color and spectral, PRF. If we change our PRF, the baseline will stay the same, but the scale will change. Now we'll have even more hash marks there. And instead of going from 0 to 50 to 100 up to 250, it will go to 100, go to 400. So this whole scale will change when you change your PRF. I don't want here, I'll just say 0 to 400 with my PR change. And then what happens is that this waveform simply becomes smaller. It becomes smaller all around. So maybe something like this. Whoops. Oh, by the way, so the waveform itself will get smaller on our screen in order to fit. While it got smaller, the scale got larger. Does that make sense? Yeah, the scale became larger. Yeah, that makes sense. So I drew in, just for the heck of it, too much. A little bit of turbulence here. You can see turbulence at the top of your velocities. You can also see turbulence down here. We call this the window. I don't want to get too much into this, but open window, meaning this area is black or hypoechoic, anechoic. Open window. Is laminar flow. Closed window is equal to turbulence, or at least suggest turbulence. It doesn't. Everything we do in ultrasound, it is very difficult to make, let's put it this way. It's very easy to make normal look abnormal. It's very difficult to take abnormal and make it look normal. So there's a lot of things that we can do accidentally on the screen to make things look like pathology. But if you have pathology, it's generally very difficult to make it look normal. So if you have turbulence, and so the example right here being, if you have turbulent flow, you cannot make it look laminar. There's no way of doing it. If you have laminar flow, there's about there's several ways of taking laminar flow and making it look turbulent. So once again, all of this skill, all this practice is for good reasons. Seems easy, but it is not. 10:41, 11. Okay, still going. We're doing well on time. I hope you guys are. By not taking a break, I feel a little bit better about letting you go early. But if you guys are dying, just say, Kurt, I can't take it anymore. Mr. S, I can't take it anymore. Okay. Yesterday, I had you guys, or several of you, I had you change your color box to straight up and down. Just because there's some rules to steering the color box that you guys don't know yet. And so I just leave it straight up and down. That way the rules aren't broken too badly. Okay, so this is a common carotid artery here. The flow in the neck, the flow on our screen is going in this direction, but it really, that's prettier. Man, let's use purple. Okay. It doesn't matter. It does not matter what I'm talking about right now when it comes to changing the box direction. Does not matter one whit about the flow direction. In the CCA, the flow is from the right side of your screen to the left side of your screen, if you're holding your transducer the right way. Does not matter though. What I'm going to tell you about does not matter. We have our skin surface here. We have our transducer here. The vector, vector is a matter of velocity and direction. The vector from this point is more or less, let's just exaggerate it a little bit. And call it there. Essentially, the blood at this part of the artery is toward the transducer. The vector from here happens to be going in that direction, but you know what? I'm going to put an arrow at both ends. It does not matter. That vector, though, is in this case, with the flow going in this direction, away, and this vector from this point, oops, let's make that perfect. Why? I'm not in the right. That's why. This vector is neither towards nor is it away from the transducer. Horrible. We have horrible Doppler when the vector of flow is parallel to the transducer itself. It will not work. Go around the corner a little bit or go even just away and the vector improves. Good Dop. And same thing over here. Smiley face. Good Doppler. Unfortunately, I'm just going to have to erase everything here. So Does that make sense? When I talk about the cop taking pictures on the side of the road, he wants to be on the side of the road with a good Doppler vector. A good vector. He wants to be more or less looking down the road, and they can catch you going towards them or away from them just as easily. We can capture blood flow towards or away just as easily. But if that cop is way off in the field and he's got his gun aimed perpendicular to the road, forget it. He cannot get a Doppler reading. He does not know how fast you're actually traveling. So steering all right, let's just quickly draw this back in. In fact, I'm not even going to draw a curved vessel. A lot of times vessels do that, and especially in the carotid, it actually starts off, it kind of comes up on the screen, on the right of your screen, and then it comes to a peak, and then it starts going down. A lot of people that happens, but I'm going to go ahead and draw a straight vessel because it's the same difference. Usually not green. Okay, there's our carotid again. And we want to start Dopplering. So if we want a Doppler over, our transducer is here, but we want a Doppler over here, we're going to put our box in. I'll put the top of the box in. But we're going to steer the box in this direction. This essentially is forcing an angle so that we're not, I want to say it this way. Well, yeah, we're forcing an angle. I'm going to draw the curved one too. I think it actually is better. We're forcing an angle this way. If I'm dead center, if I'm looking straight down, what's that, smart? And I want to look right here. If I have a box that's straight up and down, no Doppler. I have no angle of attack, and so I really can't see what's going on. So even if I'm here, I'm going to, darn it, I'm going to steer. And this time, it doesn't matter which way I steer, but I'll go ahead and steer it in the same direction. Okay, now once again, I've forced an angle between me and the road. Me, the cop and the car, or the transducer and the angle or the vector of blood. If I'm over here and I go in this direction, I'm now officially aiming my box in exactly the wrong direction. Because I'm trying to, instead of going, the vector of flow is going this way, my beam is coming down. Well, I've really drawn this in such a way that it's hard to imagine, but all right. No, I don't need that at all. Just kind of correct, so, oh wow, I still see, it's like a real whiteboard. I can still see stuff that I had before. Okay, let me do this again. Except this time, once again, with a curved, exaggeratedly curved vessel. The vector, of course, is going this way. It's perfectly flat right here. And then going this way. Vector of flow. And it does not matter. Let's put arrows on the other end. The flow could be going in the exact opposite direction. It simply does not matter. If I'm going to do a box over on this side, and if I aimed it in this direction, I've essentially negated the curve. The curve can be, you could use the curve to your advantage. Here, I've made a mistake. I've aimed it in the wrong direction. I've basically, let's do this again. I've basically made this more of a 90-degree angle from here to here. That's the exact opposite of what I want to do. I want to make it a more obtuse angle. So if the vessel is coming up on the right side of my screen, if I'm going to steer at all, I don't have to steer if it's coming up really well, but I'm going to steer in that direction. Now I've created a much better angle. There's some mathematics involved. I just don't want to get into that right now. This is a good Doppler angle. And if I'm over on this side, I'm going to want to steer more in this direction. This makes, like, if you look at there to there and then there to there, this angle here is once again a good Doppler. Here, if the vessel is basically flat and the vector of flow is perfectly flat, there's a couple of things I could do with my hand. I don't have to be stationary. We'll talk about that in lab. But I could use either one of these boxes to steer, or either one of these directions to steer. And that ends out forcing a little bit of a better, we're going to call this one okay. That's an okay angle. It's not really good. But these other angles are quite good. I kind of feel like I might have lost you. Here's the good news.
Real quick, is the angle, are we wanting it to be perpendicular to the flow in order for it to be good?
The ideal angle, the ideal Doppler angle is 0 degrees. So if I could create a box angle, well, this stuff like this actually can happen, and this is the ideal angle right here. Let's say a vessel's coming along here, and then it dives straight down, and then turns off like this. My vector of flow right here is pretty much straight away. I actually don't have to steer my color box, or for that matter, my spectral. It's actually the same difference, spectral and color. I don't have to steer it at all. It looks slightly steered, but let's just, everything's a little cockeyed. This is a 0 degree angle or steering. I'm going to put steering angle is 100% accurate. But certainly with spectral, it's 100% accurate. When we start going off kilter and we no longer, and when I say 0 degree, basically the beam's coming down and it's right in line with the blood. Whether that blood's coming this way, that way, does not matter. The steering angle is 0. You're looking straight down the barrel of the vessel. You cannot get more accurate than that. When we're starting to do imaging off like this at 60 degrees, I know what the actual value is, but I don't want to say it. Let's just say not so accurate. And the reason why we say 60 degrees, beyond 60, the inaccuracy goes through the roof. It's logarithmic, the inaccuracy. So it becomes very inaccurate very quickly beyond 60 degrees, which is why 60 is our max angle. Whoop, that's funny looking. Well, I feel like I probably lost some of you on this because I don't feel great about this. However, everything I said is going to help you. Next time we meet in lab, we're going to start talking about this, and you're really going to understand. I'm like, okay, yeah, I got it. There's nothing I said that was inaccurate. It's just, I kind of feel like, well, once again, this is the first time I've taught this particular subject on Zoom, and it's a little harder sometimes. Yeah, that's all I wanted to get to today. Didn't finish 18, but that is fine. We're slow walking it on that. Started talking to you about Doppler. This is not the Doppler talk, by the way. This is like literally just giving you something so that when we're in lab, you have a bit of an understanding of what's going on. That's all I really wanted to get to today. And we also did review, so we're in pretty good shape. And I think.
So question, would it be safe to say like to start reading, I guess, chapter 19, since that's where it talks about the Doppler?
Yeah, you can go ahead and start reading chapter 19. Just be forewarned, it's going to take, we only meet for this class once a week, and it'll be probably a few weeks before we're really back into talking about Doppler again. So you're more than welcome to read it now, but if you do, you might be more ahead of the class than you read it. It's not going to hurt to read it. Just know that we're not going to be really deep into that chapter for a few weeks. So that's just kind of the way the book is set up, and I need you to know Doppler now for lab, whereas the book kind of puts it at the end, which is backward for my needs. All right, test tomorrow. Gosh, I haven't even set a time, did I? Beginning of class. Well, no, we'll give everyone because we have people going to lab first, right? And then we have class. End of class? No, because I don't want to start teaching you something and then do a switch up and say, oh, here's your test on the other stuff we haven't been talking about. So beginning of class, we'll start class a little bit later than normally. So at 10:30, the test will go up. You will have 1 hour. Crap, we're not even going to have class tomorrow, are we? No, we're not. Okay, yeah, basically no class tomorrow. The test will be at 10:30. The open slot will only be open for like 10 minutes. So that means you have to get on at 10:30, 10:40 at the latest, and then it shuts down, and then you have to text me, and I have to be like, well, why didn't you start it? And you'd be like, oh, because. So make sure your computer is working and everything, so we don't have any kind of computer issues. 10:30. Keep saying 10:30. I better write it down.
Mr. S.
Mm-hmm.
I go into lab tomorrow, but I live in Las Cruces. It takes me about an hour to get home.
Okay.
Yeah, I was gonna ask for that. Would we be able to sit down in a classroom and take it there if we brought our computers?
I'll have to ask Melissa, and then she'll have to ask Pablo, and Pablo will have to ask. I certainly don't think that's a problem. It's only a problem if a lot of you want to do that down here. I would think that's a problem. That wouldn't be a problem, but and God, it's so much easier just to do something and then ask for forgiveness than to ask permission and then not be allowed. So if you want to do that, just bring your computer and we'll see if we can get you into a classroom. But having said that, now we're not having class tomorrow anyway. So let's just start it at 11. 11 to 12 is the time frame. Well, it's 1 hour from the start. Shit.